So, welcome to the second session of today. We continue with the topic on numerical simulations, and the next speaker is Pavel Vojvidovich, telling us about whether the semi-metal-insulator transition is conformal or not in graphene. Pavel, please.
Thank you. And I would like to thank the organizers for organizing this nice online event. We have seen in a number of talks discussions of all kinds of unusual and unconventional phase transitions and critical points and universality classes. So my talk will be also in this direction, and I will discuss what kind of phase transition can we encounter in a graphene that is close to real graphene in some sense. So I will not go very much into details about the technicalities of graphene. This is all well known so far. So we work with the standard tight binding model of graphene, which has 2 Dirac nodes per Brillouin zone. So we work with the standard tight binding model, and we do a replacement of creation or redefinition of creation annihilation operator in the standard way, where we attach plus or minus sign to electron creation or annihilation operators living on different sublattices. And after this, we obtain the standard quantum field theory of graphene, where the vacuum is the standard vacuum annihilated by fermion annihilation operators called psi, which still carries the index of spin up and down. And the charge operator now is the difference between the numbers of up particles, particles with arrow up, and particles with arrow down. So the standard representations where we go from spin components to particles and holes. And the interesting things start when we switch on interactions between electrons hopping on a hexagonal lattice. So if we neglect any kind of relativistic physics, which is reasonable because electrons travel at a very slow velocity, Fermi velocity is 300 times smaller than the speed of light. So with very good approximations, the interactions can be approximated as just instantaneous approximation, instantaneous interactions. So we can just write our interaction Hamiltonian as the product of charges at lattice sites x and y times the potential Vxy, which we do not specify yet. So we do not consider any phonon-mediated interactions. They can be argued to be irrelevant, at least if the temperatures are not too low. So early works on graphene studied inter-electron interactions either on square or hexagonal lattice and modeled interactions between fermions just by putting gauge fields on this square or hexagonal lattice. So basically, in the way in which we will also simulate, say, electrodynamics on the lattice. So here I show interaction potential that we obtain with such a discretization on hexagonal lattice. Lines with points on them show lattice potential obtained with lattice gauge fields, and the green line shows just 1/r potential from pure Coulomb interaction in the continuum. So we see that deviations are quite significant, but nevertheless, with these interactions, people did a lot of work and came up with a very attractive scenario that strong interactions can open a gap in graphene. And antiferromagnetic ordering is the main channel for spontaneous breaking of lattice or sublattice symmetry. It was actually borrowed from considerations based on the picture of on-site interactions. And it's it's probably worth explaining why opening the gap in graphene is important. If we can open the gap in graphene in some clean way without affecting the charge carrier mobility, this will open a way to produce high quality superconducting semiconducting devices with graphene and open up a lot of technological applications of graphene. So this is not just purely academic reason. So then around 2011 and 2012, experimental group in Manchester performed very accurate experiments and put an upper bound on the size of a gap in clean suspended graphene, which was less than 1 milli-electron volt. So really a small gap. So with a very good precision, we can say that clean suspended graphene in nature is still a semi-metal. So for some time, this was quite puzzling because all numerical simulations pointed towards a scenario in which the gap should be very sizable, much more than 1 milli-electron volt. Until around 2013, it was realized that screening of Coulomb interactions at short distances plays quite an important role. And on this plot here, you can see the comparison between the standard Coulomb potential in the continuum and the interaction and the inter-electron interaction potential in graphene calculated within the random phase approximation by Welling. So we see that especially at small distances, the deviations are very sizable, up to a factor of 2. And in particular, we also have quite a small value of on-site interaction, less than 10 electron volts. Whereas if we just do lattice gauge theory discretization of interaction potential, this number is just some lattice artifact. It's very large. So if we use this realistic interaction potential for Monte Carlo simulations, then the semi-metal-insulator phase transition is shifted to unphysically large interactions, and we obtain a good agreement with experiments. And a nice illustration for how well numerics can agree with experiment was shown yesterday in the talk by Maxim Ulybyshev, where he has really matched using this interaction potential Fermi velocity renormalization with very high precision. And in the meanwhile, around 2015, people found a purely technological way of getting graphene a good gap without affecting charge carrier mobility. It was just achieved by putting graphene on a substrate in a special and clean way, and this basically solves this technological problem. So one can think that the story is pretty much clarified. However, if we think about it accurately, we can realize that most of the studies only tested antiferromagnetic ordering in real graphene. And further, most of the studies introduced a special bias, like a source term, to facilitate this spontaneous symmetry breaking in a finite volume, which cannot happen otherwise. So it still makes sense to check what maybe other phases we can realize. So if we check the literature for possible phases of interacting electrons on hexagonal lattice in the presence of arbitrary interaction potentials, there are a number of interesting predictions. For example, if we allow for nearest neighbor interactions, here denoted as V, in addition to on-site interactions denoted as U, we can have, apart from semi-metal and antiferromagnetic phases, which are very well studied by now, we can also have a charge density wave order, which was not really studied for real graphene. And if we allow for also next to nearest neighbor interactions, we can have other interesting phases like quantum spin Hall effect and all other phases that exist also for purely on-site interactions. So we can also, it was conjectured that sometimes we can also have spin liquid phases, Kekulé distortion phases, and a lot of interesting phases. So it is interesting to check whether our real graphene can be somewhere close to this, to some of these interesting phases. So that's why we decided to revisit the phase diagram of graphene and check at least the most probable option for non-antiferromagnetic ordered phase, because previously we were only looking at one order parameter. And if our lattice setup is indeed reproducing the phases of graphene, it can be still useful to somehow understand how close our physical point can be to some phase transition line. Is it a phase transition to antiferromagnetic state or maybe some other state? So people who work on QCD here may think of what is known as Columbia plot for QCD phase diagram, where we know that the physical point lies in the region outside of any phase transitions, in the crossover region, but nevertheless, people invest a lot of effort to characterize all possible deviations from physical parameters to make this Columbia plot as precise as possible. So in particular, if we know how close we are to one or the other phase boundary, we can obtain useful information about fluctuations of order parameters. It is also important for convergence radius of perturbative expansions, because convergence radius will be limited by the nearest phase transition, nearest singularity. And we can also learn something about most likely channel of symmetry breaking upon small deformations of our interaction potential, which can be achieved, for example, by stretching graphene or some other deformation. We want to be as unbiased as possible in our study, so we want to avoid any source terms that might favor one symmetry breaking channel over another. So as I mentioned, with a realistic graphene interaction potential, this potential Vxy is such that graphene is a semi-metal. So we introduce some artificial coupling constant lambda and change it to check how we should increase lambda in order to enter some non-trivial ordered phase. And also it was not checked properly that we are not in the charge density wave phase already at lambda equal to 1. So only antiferromagnetic ordering was checked so far and no charge ordering. So now if we want to simulate without source terms, this is pretty much like simulating massless QCD in the language of lattice gauge theory, which is known to be very hard because of determinant zeros, which prevent us from being ergodic. So in particular, if we use hybrid Monte Carlo, we evolve along a reasonably smooth trajectory in configuration space, and determinant zeros act as potential barriers which do not allow this smooth trajectory to go into another region of the phase space. And it is indeed an issue for hybrid Monte Carlo with real valued Hubbard field, where we cannot really turn our source terms to zero without encounter ergodicity issues. So to avoid this, we use complexified Hubbard-Stratonovich fields. It is enough to complexify only the Hubbard-Stratonovich transformation for on-site interaction, so denoted as Vxx here. So we rewrite our Vxx times charge squared term as some coefficient eta times this terms minus 1 minus eta, again Vxx times spin operator squared. And spin operator differs from the charge operator by the plus sign instead of minus between the number operators for quasiparticles with spin up and spin down. So then for the for the term which involves charge squared, we apply the standard Hubbard-Stratonovich transformation, which was applied in all basically previous work on the subject. And for the term with spin squared, we apply another Hubbard-Stratonovich transformation where the integral is explicitly real. There is no imaginary unit in the exponent. And if we then integrate out fermions, we arrive at a path integral representation of a partition function where we have integrals over two Hubbard-Stratonovich fields, phi and chi, which enter the two determinants for like two particle and whole states as a single complex Hubbard field, which takes complex conjugate values in one and the other determinant. So as a result, the product of both determinants is still manifestly real. But now, since we run our hybrid Monte Carlo in a higher dimensional space, we can easily go over these potential barriers, because now the barriers has lower dimensionality in comparison to the space where hybrid Monte Carlo is allowed to move. So we solve ergodicity issues, and this can be checked by performing very precise measurements and comparing them, say, with exact diagonalization and other methods like BSS QMC. Now we also implement a number of other algorithmic improvements, like we do not want to work with sparse matrices as we usually do in lattice QCD simulations. It turns out that it is advantageous to work with full dense matrices, like matrix exponents of single particle Hamiltonian and exponents of the Hubbard fields. And furthermore, instead of stochastic estimators, we calculate fermionic forces exactly. So we do not use stochastic estimators. All this requires a lot of operations with dense matrices, but of course, we spend some extra time on those dense matrix multiplications, but nevertheless, this gives us some advantage and allows us to speed up calculations in the end. So in particular, if we look at the fermionic force in hybrid Monte Carlo calculation, we see that if we use stochastic estimators, fermionic force is a wildly oscillating function. But if we use exact fermionic force estimation, it is quite a smooth function, and to plot it on the same scale, we had to multiply its magnitude by 100. So it's 100 of times smaller than those oscillations, and as a result, we can increase our integrator step in hybrid Monte Carlo by a factor of 50 or even more. So, and this pays off for the extra effort that we have to invest in working with dense matrices. So, in particular, those techniques also allowed to go to very large lattice sizes in the simulations which were discussed by Maxime yesterday. So now, after discussing these algorithmic improvements, let me discuss what exactly we measure. So since we introduce no sources that favor formation of condensates, we have to measure observables that are related to fluctuations of order parameters, and our observables are related to sums of charge on a particular sublattice and sums of spin on a particular sublattice. So we separately sum local charge operators and local spin operators over the two sublattices. Then we square both sums and add them together. So if we have some spatial modulation where some site will acquire either non-zero spin polarization or non-zero charge, then this order parameters, these quantities will be large. But if those quantities are, these fluctuations are thermodynamically irrelevant, if they do not correspond to any condensate that forms in the infinite volume limit, then those quantities will just extrapolate to 0 in the infinite volume limit. So we use lattice sizes 6 by 6, 12 by 12, 18 by 18, and 24 by 24 in our simulations. We use boundary conditions that correspond to rectangular compactification. It's like a toric nanotube made of graphene. Tips of the Dirac cones are always covered by our discrete lattice momenta, so we can be sure that we have those massless fermionic modes that are important for the physics of graphene. We use 128 Trotter steps with a size of hopping times Trotter step equal to 0.17. And we produce several hundreds of configurations per data set using binning to calculate statistical errors and take into account autocorrelations. So first we check which order is really preferred in a physical graphene by considering the difference between antiferromagnetic state and charge density wave. So away from the phase transition, we can parameterize the volume dependence of those of those order parameters as expansion in 1 over the lattice size. So the leading term is just a constant, which corresponds to non-zero condensate, and the next leading term is some coefficient over the lattice size. So this ansatz is expected to work away from the phase transition. So if we look at charge density wave parameters, then it appears that the lattice size dependence of this order parameter perfectly extrapolates to 0 for all values of the couplings that we consider. So we conclude that charge density wave condensate is thermodynamically irrelevant, and it does not correspond to any condensate that might form in the infinite volume limit. On the other hand, if we look at the antiferromagnetic state order parameter, the spin squared, we see that starting from lambda equal to 1.6 approximately, we develop some non-zero expectation value. And we can plot expectation values of both charge squared and spin squared extrapolated to infinite volume as a function of lambda, and we see that while for the charge density wave, the extrapolation fluctuates around 0 within error bars. For spin density wave, we observe a formation of non-zero condensate starting somewhere from 1.6 by 1.65. So next, we aim to study critical scaling and determine whether we deal with the standard second order phase transition. So we use the standard scaling ansatz and first try to obtain the intersection plot to find the critical lambda, and then we, having a critical lambda, we try to make a collapse plot by choosing this critical exponent nu to be as close as possible to yield the best collapse plot. So since we want to compare our results with the data for purely on-site interaction for the Hubbard model on hexagonal lattice, we used a BSS algorithm to obtain results on the same lattice sizes with purely on-site interaction. And then we obtained our estimate of critical exponents. The ratio of beta over nu is equal to 0.812, and nu is equal to 0.928. And if our graphene is indeed in the same universality class as the Hubbard model, then with these critical exponents, we should presumably obtain a nice collapse plot. But this doesn't quite work, and this is the best collapse plot that we can obtain. So you still see quite strong deviations from a single line, and intersection plots look even worse. So if on the other hand we look at the data for the Hubbard models, and we see a perfect intersection of different data sets upon rescaling with this critical exponents, and also a good quality collapse plot. So then, okay, our conjecture doesn't work. It seems that the data for Hubbard model is not quite close to the data for graphene, and we set out to determine the critical exponents from scratch. So this gives us the estimate of the ratio of beta to nu equal to 0.967, significantly more than for Hubbard model, and the critical coupling of around 1.7. With these parameters, we can obtain some collapse plot if we assume that our value of critical exponent nu is 1.473. So this is significantly larger than for the chiral Gross-Neveu universality class expected for the Hubbard model. So it seems we obtain the results which are really different from what we could get for the chiral Gross-Neveu universality class. So somehow we can also think that maybe the deviations lie on the Hubbard model side. So maybe a Hubbard model has very non-universal scaling, and our value for those non-local interactions are actually close to a normalization group prediction, which is beta over nu equal to just 1. But then our result for the critical exponent nu is still significantly larger than renormalization group prediction of 1.2. So somehow this assumption is also not quite consistent. So we just want to check then how our data actually constrains the values of a critical exponent nu. And to this end, we show the deviations of different data points from like the scatter, the characterization, how much different data points scatter on the collapse plot, this chi-squared, as a function of the critical exponent nu in the feeds. And for the Hubbard model, we see that once we deviate from our estimate by, say, 0.1, chi-squared reaches values of 10 or 20. So the data appears to be quite well constrained for the Hubbard model. But if we look at graphene results, then we immediately notice that the scale for this chi-squared is significantly smaller. And in particular, if we only look at the data for large lattices, it appears that the values of critical exponent nu are not constrained from the side of large nu at all. This is a very shallow plot, whereas it quite strongly excludes the value of 1.2 that is dictated by a renormalization group analysis. So at this point, we can conservatively state that it appears that if we try to rescale the data for graphene, for realistic interaction potential in graphene, it appears to be very different from the Hubbard model data. So then we can go on and try to conjecture what it is, what we might really observe. And our conjecture here is the scenario which is called conformal phase transition. I think it will be also discussed in a number of talks at this workshop. And let me present some considerations in favor of this scenario. So to start with, conformal phase transition is not a finite order phase transition, rather it corresponds to an essential singularity in the order parameter. So all derivatives of order parameter with respect to coupling at the critical coupling are equal to 0, but nevertheless there is a singularity. So this is a function which characterizes such a scaling called Miransky scaling. And in particular, it was worked out that conformal phase transition might happen in massless QED in 3+1 dimensions and in 2+1 dimensions, where the control parameter is the number of flavors. And graphene appears to be just in between the two cases, because in graphene, gauge fields propagate in 3+1 dimensions, but fermions propagate in 2+1 dimensions. So it is not unreasonable that we can somehow realize also the scenario of conformal phase transition in graphene as well. And then if we look at the correlation lengths, then at conformal phase transition, correlation lengths also diverges as an exponential of inverse coupling. Basically, it's also essential singularity. And it's obviously growing faster than any inverse power, so any finite value of this critical exponent nu. And on the other hand, in a finite volume, conformal phase transition often looks like a second order phase transition, and one observes power law scaling with some corrections which do not quite fit into a second order phase transition picture. It was shown by Gamayun, Gorbar, and Gusynin in 2009 that formally conformal phase transition corresponds to a limit where the critical exponent beta tends to infinity and nu tends to infinity, but hyperscaling relations may still hold with a critical exponent of delta equal to 1. And in our case, d is equal to 2, the number of spatial dimensions, so the ratio of beta over nu should be close to 1. And this agrees well with our result, which yields beta over nu equal to 0.967. So this is one argument in favor of this scenario. Then if we indeed try to show intersection plots with beta over nu equal to 1, we also see good quality intersection plots. And then we want to check whether what we see is can be described as a second order phase transition. So generally for a second order phase transition, the slope of this function order parameter times L to the power of 2 beta over nu will go to infinity as we go to the infinite volume. So we will see a singularity. So on this plot, we show the inverse slope as a function of inverse lattice size for the Hubbard model data and for real graphene. So we see that for Hubbard model, the inverse slope appears to approach 0 much faster. And the data for graphene can also be approximated with a power law dependence, but the critical exponent nu again appears to be quite large, 1.6. But also with a good high squared, it can be also described by a function which has a finite intersection at L equal at large lattice sizes, so a finite value. So we can basically make a fit with constant plus some coefficient over the lattice size, and the intercept appears to be non-zero. So this points out that the slope can be finite as we go to thermodynamic limit, and this can never happen for second order phase transition. So high squared for both fits are below 1. So really, we can only say that our data is consistent with both scenarios. And basically, all our evidence is at the border of statistical significance, which is expected for conformal phase transition, as it is very difficult to catch in a finite volume simulation. As one last argument, we tried also to feed the lambda dependence of our order parameter with a Miransky fit, and we obtain the critical lambda, which agrees very well with what can be obtained from intersection plot. So somehow the conjecture that what we observe is a conformal phase transition appears to be somewhat more consistent than the picture of second order phase transition. But of course, it's only a conjecture, and it would be very nice to see some input from larger lattices or alternative simulation methods. I don't know, maybe like tensor networks or diagrammatic Monte Carlo. Let me just note that conformal phase transition happens naturally in a system which combines long-range Coulomb interaction with on-site interaction. It was analyzed a long time ago in this paper by Miransky in 1996. So they conjectured that if we make a phase diagram in the space of purely on-site interaction and Coulomb interaction, we observe a line of second order phase transition which starts from zero Coulomb interaction, but then at some point it can turn into a line of conformal phase transition, and if we just work with pure Coulomb interaction, we should observe a conformal phase transition, basically because Coulomb interaction is conformally invariant. It has no scale in it. So then let me come to my conclusions. We performed a scaling study of graphene with realistic interactions, which were rescaled by some factor lambda. So this construction is not merely our invention. In particular, if one wants to study graphene using, say, diagrammatic Monte Carlo, then one would also need to introduce this fiducial factor of lambda to count powers and perturbative expansion. So we find that the critical lambda is 1.61, which is quite far from lambda equal to 1. So graphene appears to be reasonably far from the phase transition. So we made no bias towards a specific symmetry breaking channel, but nevertheless, we observed a clear signature of antiferromagnetic ordering, like for the Hubbard model. And charge density wave was ruled out for our potential. So it would be also interesting to check other orders. So we only implemented 2 order parameters. But other orders typically require different hierarchy between interaction potential on-site, nearest neighbor, and next to nearest neighbor. Typically, exotic phases appear if we make either nearest neighbor or next to nearest neighbor interactions larger than on-site interactions, which is unnatural in physical graphene. It would be potentially interesting to consider theoretically pure case of pure Coulomb interaction without any screening, plus on-site interactions, and try to map out this phase diagram in a Monte Carlo simulation or some other first principle simulation. And let me also mention that conformal phase transition is often discussed in high energy physics. Of course, the most important example is just QCD, where conformal phase transition, if you wish, is located at G equal to 0. And when we take continuum limit in lattice QCD simulations, we try to approach this conformal phase transition as close as possible. But also conformal phase transition is important in scenarios such as walk-in technicolor for physics beyond the standard model, where Higgs particle appears as a technidilaton. And also, if we study phase transitions with respect to the number of flavors, then we may also encounter such a scenario where phase transition with respect to NF will be a conformal phase transition. So this is all what I wanted to say, and thank you for your attention.
Yeah, thank you very much, Pavel, for this very interesting talk. So I clap for all the... I assume there are questions.
Yeah.
Yes, maybe Simon was first.
Oh, hi, Pavel. I have I guess it's just a small technical question. You introduced a parameter eta near the beginning. I guess, to somehow distinguish between the two different competing orders. And then you gave a value for it.
Yeah, let me just, you mean this slide?
Yeah, I mean, I guess all your conclusions should really be independent of eta. And I'm just asking,
Yes.
did you check
Yes,
that?
yes, we have checked this. Yes, it's independent of eta. So basically, this is just another way to introduce Hubbard-Stratonovich. So in particular, I want to stress that non-zero eta in no way favors one order over the other. So it's not like that since it's couples to spin, it favors somehow spin ordering. No, it's so we confirmed also using exact diagonalization that and BSS algorithm that the results are very precise.
I guess one other thing is that you said you had a toric boundary condition. So yes. it was really a carbon nanotube, and I know Timo Lade and his collaborators take this idea very seriously and study the dependence on the size of the tube. Is that something you've thought of doing? No?
Well, in a sense, we were changing the size of the tube, but in some special way. Yeah, but I think for real nanotubes, the order of sizes are much, much larger than what we had.
Yeah, Lucas also has a question.
The value of nu that you compared with, I mean, of course, I understand that one value you compared with were your own simulations for the Hubbard model. But at some point, you also compared with some RG calculation.
Yeah.
The first small question is, what kind of calculation is that actually? This 1.2?
I think it's just simple one loop RG.
Yeah, because I mean, the point is that this number, I think, also has a large error bar. I mean, if it is really like one loop, then there, I mean, now there are many more results on that. And I think if I just compared with like 4 loop calculations, which also have their own error bars by Michael Scherer and Peter Marquardt and others. And I think that number actually is actually much closer to your number. I mean, I might have made a mistake here, but it's definitely above that 1.2. And I'm just wondering whether, I mean, somehow it seems not really inconsistent with this RG prediction, considering that all these predictions have large error bars.
Okay. Yeah, then maybe I should check the latest status.
Yeah, I mean, if you don't find it, but you can just write me an email or Michael Scherer.
Yeah.
There are lots of numbers now, and I think some of these numbers will definitely compare with your numbers. But the question really is which ones are the most reliable, and that of course.
So that's why we actually produced this data set using exactly the same lattice sizes with on-site interaction, because then we can be sure that we compare like the same system, and systematics is reasonably close to.
Yes.
So what we can say is that what we see with this lattice sizes, what we see for Hubbard model, and what we see for real graphene looks quite different.
Yeah.
So this is like conservative conclusion.
So maybe one question on that. I mean, if this is really a conformal transition, then you would expect that somehow your correlation length should go, your correlation exponent should go to infinity if you go to thermodynamic limit. Right?
Yeah,
I mean, and somehow you should see some drifting of this correlation length exponent. Well, assuming that if you were able to go to infinite lattice sizes, that somehow you would see that nu goes to infinity.
Yeah. So in a sense, we do see this drifting with our small. Well, we have small lattice sizes, of course, but if we exclude smaller lattice sizes from our analysis and work only with, say, 18 and 24, then we do see that the value of eta that we obtain in our feeds drifts towards larger values. So,
value of, of eta or nu?
Sorry, it's eta. The divergence of correlation lengths.
Correlation length. I see. Yeah. Okay, there you really see a drift. Okay.
So it would be interesting if we could invest more computing power in, say, 30 by 30 lattices. Probably it will go even higher.
I see. Okay. Yeah. Okay. Thanks.
Yes, and another question by Joseph.
Yeah, so I was just wondering, so this conformal phase transition, in the RG sense, you often get it when you have this annihilation of fixed points, right? So
yeah,
you have maybe some conjecture of are there fixed points that you could identify? Like, could it be something like the Grosvenor fixed point is there initially, but then it collides with some other fixed point?
That's a good question, and I think to answer this question, it would be interesting to make some study of phase diagram in the space of all possible interaction strengths. But I think this is hardly viable with Monte Carlo. So maybe some mean field calculation can just give some quick hint, but with Monte Carlo, it's very difficult to scan through higher dimensional phase diagrams. So that's why it's hard to say, unfortunately. Okay. So the very simple picture that we were looking at is just this two-dimensional phase diagram. And I think even if we set out to check this phase diagram, it would be difficult enough.
Okay, so this was not an RG study. This was...
Yeah, this is one of the first RG studies, I think.
Okay, so this is an RG study, this work here.
Yeah.
Do they discuss it in the language of annihilation of fixed points in this context, or
no?
Okay, interesting. Okay, thanks.
Yeah, so thank you very much, Pavel. It was really an inspiring talk. Very interesting results on conformal phase transitions. We have to move on to the next speaker. Nikhil Karthik, are you around? Oh, yes. Yes, now it's full screen. Perfect. Yeah, so welcome to the last talk of today by Nikhil Karthik. And it's about lattice investigations in Flatland, again on infrared conformality, but now with topological defects.
Hello, everyone. And thank you, Simon, and other organizers for inviting me to give this talk today. So this is instead of, so as the title suggests, so this will be the investigations of what happens in the infrared for these quantum field theories that live in a flatland at two spatial dimensions at one time. So this is a set of work that I did with Rajamani over some years. And so in this talk, what I will do is kind of try to summarize what we have learned till now through such lattice simulations of these systems. So this is what I aim to do in this talk. So I want to focus on two aspects of these theories that live in 2+1 dimensions. One interesting aspect is simply what are the fixed point structure in these quantum field theories, especially in gauge theory sectors. So the question that we are interested in asking is, can we produce a map of what parameter space, for example, what color and what flavor of massless fermions theory is conformal, like where the mass gap emerges and so on. So this is one question, and I will, as I will discuss, we find that the QED3 without any monopoles seems to be conformal for all flavors. And now the question is, what we have tried to do is, can we understand why non-compact QED3 kind of doesn't want to open up a mass gap in the infrared, in simpler terms. And the other aspect of these 2+1 dimensions, of course, is the topological aspects. And when I say topological, one could think of in terms of TQFTs, but it's harder to do. But one question that you can ask on the lattice is, if at all we want to do a TQFT, we want to know how to put a Stern-Simons theory on the lattice, how would we go about doing it? Of course, once I've said how to do it, I wouldn't be able to actually do a Monte Carlo simulation because it has sign problem and so on, but at least for proof of principle, can we do it? And related to other topological aspects could be, for example, about the topological defects in these theories, which are like the monopoles, vortices, and so on. So what are their properties in the infrared? What are the scaling dimensions and so on? And also, can we use lattice to study the consequences of these highly interesting new particle vortex dualities that are being discussed these days? Can we use lattice to study these conjectural theories and kind of try to see whether they hold true or not? So these are the different things that I will try to cover. So to start, so what is the theory that I'm interested in is I will talk about these gauge theories, which are coupled to massless fermions. So let me take the example of QED3, for example. In that case, I'm interested in the parity invariant theory. We'll have n little n flavors of coupled to a two-component fermion, n such two-component Dirac fermions coupled to a Dirac operator T slash, and then another such n flavors of two-component fermions which couple to minus D slash dagger. In the continuum, the Dirac operator is anti-Hermitian, so it's equivalent to just coupling it to D and D slash. But in the lattice, once you UV regulate this theory, there is a difference between D and D slash, and one has to be careful. And only a regularization in this form can parity invariance be guaranteed even at finite lattice space. And of course, there is a gauge action, which with the coupling 1 by G square, and in 2 + 1 dimensions, this coupling G square has mass dimension 1. So which is actually making the work simpler for us because scale setting is simple. What we want to do is we'll put this theory on a littler lattice, measure everything in units of G square, which has mass dimension 1. So measure G square L, keep that fixed. And then at fixed finite volume, we want to first take the lattice spacing going to infinite. Lattice spacing going to zero limit. So I have to first remark that, so this is quite important. And there's a difference between the kind of studies that were discussed yesterday when a condensed matter physics application, where one is looking for a transition, a lattice transition as you tune the couplings from different values, whether there's a second order transition or not. So that is not what we are doing here. So what we are doing here is using lattice as a simply an ultraviolet regulator. It is like any other regulator, for example, a 4 - epsilon dimensional regularization, for example. So it's just a UV regulator for the quantum field theory that we're interested in, and we want to remove the regulator first, and then study what happens in the quantum field theory at the long distance behavior of the quantum field theory. That is what we are interested in this, and lattice is simply a regulator. And so it's quite important to keep this in mind. And once we have this theory on the finite volume, what we want to do is we want to change the finite size box size and see how things scale. And that has and a large enough box sizes once that we will be sensitive to the IR physics, and we want to extract the information on the IR physics. And when I say IR physics, what we are typically interested in, for example, is a 2-point function in this. Once first you take the continuum limit, look at the 2-point function, and look at the large distance behavior of these 2-point functions, and what are the properties of that. And also because we are studying this taken continuum limit at the trivial Gaussian fixed point, not in any non-trivial fixed point. So there are no such, these are all like 4 Fermi couplings and so on that was discussed earlier in this talk today are irrelevant operators at the Gaussian fixed point. And so these is just at the bare level, these are all these couplings. It's just like 3 + 1 dimensional QCD simulation, for example. So what the question that has, for example, 30 years 30 or 40 years ago, is that what happens to the infrared properties? It so happens that at large n number of, when you couple this QED3 to large number of flavors, there happens one can show rigorously that there is a infrared fixed point in these theories. So the situation is quite different from, for example, in 3 + 1 dimensions, where the one is interested in the theory doesn't have any dimension full coupling, but why does QCD have a scale? Here it's kind of the reverse here. The theory has a dimension full coupling, and so why does one even expect a conformal behavior to set in? The idea goes back to, for example, in these papers by Appelquist et al., is that in the infrared, the induced gauge action from the fermion leads off as some non-local conformal gauge action like F and the Laplacian -12, F mu, which is dimensionless, and then the coefficient is some n/2. As you take n to infinite, this term starts dominating over this dimension full coupling, and so on, sees the onset of conformal behavior. So this is the reason why there is a conformal behavior in the large n limit. And so the question that's interesting to all of us is, as you take the large n limit, of course, there is a large n infrared fixed point. that's rigorously argued. But what happens as you lower the number of flavors, as you go to smaller and smaller flavors, typically n is of order 1, is it possible that this argument does not hold true anymore? That the scale or the conformality in the infrared is lost. And typically, the modern understanding is that at some point, at some critical flavor, some higher dimensional operator, which is naively irrelevant in the UV, but becomes relevant at this new fiducial infrared fixed point, and then gets rippled, and you develop a mass gap, and you see some particle spectrum in the infrared, or develop a condensate, for example. So this is the question, and we want to understand using the lattice as well. So for the case that I'm talking about here, which is the symmetry that is in these systems, is the SUN flavor symmetry. So if there are n such massless fermions, if there is a SUN flavor symmetry, and so this at large enough n, this SUN is unbroken, and there is a conformality, and so you would see correlators as some power law behavior, and these are the scaling dimensions that characterize the CFT, and also these bilinear condensate will be 0 in that limit. And as you lower the number of flavors at some critical flavor, this SUN will get broken down into some SUN where half n is half the n, and another SUN, and then so there's a flavor symmetry breaking, leading it to some ion physics in the infrared, and you would see the true point functions to have a mass gap and lead off as some exponential decay at large enough distances, and these condensates will have a non-vanishing value. So this breaks the SUN flavor symmetry, and so it will have a BEV. So this is the point, and for what is the typical value of n in the infrared? That has been the question, and there have been previous studies by Simon and others, and where there was indications that the n could be as small as 1 or so. But as I will discuss in our study, I'll discuss this study in our case. And recently there were even computations of these large n scalar dimensions by Sylvie Prufu et al. And they found that it's possible that these 4 Fermi operators never become relevant in the infrared. And so it's possible that the QED3 could remain conformal for all values of n. And also need to point out that in QED3, there are these operators that you can insert are, for example, bilocal operators, composite operators in fermion, for example, like this. And also in addition to these simple bilocal operators, you can also have a monopole operator, so like topological defects, which are highly non-trivial in terms of these fundamental fields that enter the quantum field theory, but they nevertheless behave as though they are point operators. In these theories. For example, in QED3, it's a monopole operator of charge Q is defined through its action that once you insert it, its action is to put in any surface that encloses it has a non-zero flux, which is equal to this 2 pi Q. Yeah. So this is the lattice typical. So just the details of how to do this calculation is to regularize on the lattice. So you divide this, you put the system on a finite physical box size of little L cube, and then you put it in a capital L cube lattice sites. And then these gauge fields live on the links and the fermions live on the sides. It's all regular. And then, so once you have this on the lattice, so the continuum limit is that you fix the little L and take capital L to infinite. So I talked about this gauge action, and there are 2 ways to do it for the abelian case. One is that the non-compact way of doing it, which is a U1 theory. So the gauge group is still U1, not R. It's a U1 theory, except that there are no monopoles that appear in this in the continuum limit for these theories. So this is typically called a non-compact. So it should not be thought of as R gauge field. So U1 gauge field. And then in these theories, because there are no monopoles, the flux which on these time sliders are conserved, and that is typically called the U topological flavor symmetry. It's the U1 topological symmetry is conserved in these theories. And or I can put a compact gauge action, which is, for example, like cos of F meaning studied by Polyakov, and where these monopoles are allowed and flux is not conserved in these theories, and it typically confines. And non-abelian theories are simple Wilson gauge action that we all know. And for the fermions, we regulate the theories using both Wilson and overlap. So in this talk, you can simply think of it in terms of overlap fermions. So I'm not going to the details. So what is pertinent for overlap fermion is simply that the overlap. So using that fermion, you capture the determinant of the fermion through such a term, That's the determinant of 1 plus V times 1 plus V dagger, where V, all you have to know is that it is written in terms of a Wilson operator, and it's a 2L³ by 2L³ unitary matrix. That is the essential property that V dagger is 1. So a lot of interesting properties come out of it. And the point, and in addition to that, the propagators enter through the generating function here, where these G's are the propagators of the 2-component fermions. So as though even so, to not see the U2 flavor symmetry of this of NF equals to 2 theory that I've written here is that it's quite manifest seen here, because this part is exactly U2 invariant, and all propagators and so on will be exactly UN invariant, and so even at finite lattice space. So this is the essential property. I'll come back to, if I time permits, I'll discuss some interesting property simply because of these unitary operator. But this is the simulation that we have to do, wherein we do this using the HMC. So, but those are technical details. I'm not going to go into that. So once we have that, so we put this theory on the lattice and we do the simulation. What the quantity that's quite interesting is to look at the eigenvalues of the Dirac operator itself. It has a lot of information on the infrared physics. Or in other words, you look at the eigenvalues of this inverse Dirac propagator, which is G inverse. So these are the eigenvalues of this operator arranged by their magnitude. These are called the microscopic eigenvalues. And because we are putting it in the finite volume, these are not 0, these are all gapped. And so it makes sense to talk of them as though it's 1, 2, and 3, and so on. Once you have ordered it, we first take the continuum limit. We fix it in the box size to be little l, and then you simulate a multiple set of capital L's for the little l, and then take the continuum limit first. So for example, you take lambda j, capital L, and you take the limit L to infinite, and then you recover what you estimate to be the continuum values of these eigenvalues at a given value of finite box size. One such continuum limit is shown here, for example, for a lambda for the lowest eigenvalue for the overlap operator, and so at different little l's. So once you have the continuum limit, you can now ask, what happens to the continuum eigenvalues as you take the box size to infinite? And that's where the conformality comes in. If the theory is conformal, then you expect these eigenvalues to scale as some L to the -1 minus gamma S. Gamma S is the mass anomalous dimension of the theory, if it is conformal. For example, take the free theory, the mass anomalous dimension is 0, so lambda simply scales 1 over little l, which is well known because it's just 2 pi by capital L kind of behavior. And on the other hand, in the broken side, when it's broken down to some lower symmetry, the pion physics comes up, and we know from Banks-Kasher relation that there is a finite density of eigenvalues, which directly imply that these low-lying eigenvalues scale as the inverse volume of the box, and it goes like 1 over little l cubed of the box size. But this is simply Banks-Kasher, but we can make complete use of the pion physics by resorting to what happens to chiral Lagrangian in a finite box. Then it leads to this concept of random matrix theory description of the eigenvalues, low-lying eigenvalues. Simply put, the point is when you put the chiral Lagrangian in a box size, the spatial fluctuations become unimportant, and only the fluctuations in the pion field itself is important. So that simply means that there is a matrix model which is governing the theory in a finite box. In a small enough box size, when the Compton wavelength of the pion is larger than the box size itself, which is typically the case for the massless limit. And so in that limit, what happens is so that typically for a lot of people like Lloyd Feller and Ferberschott and others found that this matrix model behavior means that the distribution of the low-lying microscopic eigenvalues of the Dirac operator are again captured simply by a random matrix model, which shares all the global symmetries of the theory itself. For example, in the case of QED3, it goes by the name of non-chiral Gaussian unitary ensemble. And so you simulate that model, so you get these Z's, which are these eigenvalues from the random matrix model, and then these lambdas are the eigenvalues of the Dirac operator, and so the scaling as Zi by lambda I L cube in the large L limit will tend to a non-zero vanishing value, which is nothing but the condensate in the theory itself. So if so you can define it. So only in the infinite volume limit, this will be a finite number, and more powerful is that this value will not depend on which eigenvalue that you used to determine it. All the eigenvalues have to go to a single non-zero vanishing value. So that's the condensate. So that's a pretty powerful statement. And this is the technique that we use to determine the eigenvalue or not. So I'm looking at whether it's this behavior or this. So here is one typical example using the large N, the Tooth limit in this large N C limit of the parity invariant sector. So these are the distributions of the eigenvalues. So these red, green, and blue are these individual microscopic eigenvalues of the Dirac operator, the Tooth limit, and is compared with these black curves, which are the predictions from the random matrix theory, which has the same symmetry as that of the large N QCD. And as you see, this nicely follows all these data points. And from this, using these relations, you can get a value of the condensate itself in the Tooth limit. And certainly, you do expect a non-vanishing condensate in the Tooth limit, because you'll never be able to get rid of the confinement scale. So now, using this, we scanned the whole region of a phase space on this parameter space in this gauge sector. So one axis is the number of flavors of massless fermions, and on the other axis is the number of colors that is there. So we did it in U1 theory, SU2 theory, and even the Tooth limit. And these control cases, which are the cases where you expect the condensate, and just to check that indeed the method works. First, to demonstrate that it's okay, is these horizontal line, which is the quenched case. And we demonstrated that indeed there is a condensate. And the Tooth limit is another case where there has to be a condensate, and we found that there is a condensate, as I described to you in the last slide. So the case, and for SU2, there is a critical number of flavors, and it seems to be that it's around above 4, and more work is required in that case in order to clearly rule out 6 or not. And this might have consequence for the SO5 emergent symmetry that was discussed today, because the N equals 2 SU2 theory seems to be the effective theory that's being discussed in that scenario. And if there was SO5 symmetry, my understanding is that this SU2 theory, N equals 2, has to be conformal. But in our simulation that we found here, that it's scale broken. So what is more interesting is the U1 sector. So I'll explain the N equals 2 theory in a more as an example. So here, what I've shown here is this, again, the distribution of the low-lying Dirac eigenvalues, first, second, third, and fourth. And and at the different points are changes in the volume, the physical box size, not a capital L. It's the physical box size measured in units of G square. So larger the value means larger the physical box size. And so these are this, as you see, there's not much movement coming because of the increase in the box size. It's almost saturated. And it's compared with these black curves here, which are the predictions from the random matrix model that has the same symmetry as the N equals 2 QED3. So these are these black curves. I showed you that in the large N limit, it exactly passes through it because there is a condensate, whereas this is the exact opposite behavior. So there is no agreement with the random matrix model, suggesting that maybe there is, again, first hinting that there is no condensate in this case, possible, or at least possible. And another way to look at it is in terms of these condensate that I defined in the last slide, which in terms of these random matrix eigenvalues divided by lambda time divided by L cubed. So that's so these curves here, the red, blue, and the pink ones are the condensates at finite volume. The x-axis is 1 by little l. So these are condensate at finite volume determined from the first, second, third, and fourth eigenvalues. And there is no reason why they all have to agree at any finite volume. They only have to agree in the infinite volume limits. So you do some extrapolation, assuming there is some 1 by L square corrections and so on. So that fits it well. And then you extrapolate it down to 0, you find that it's quite consistent with 0, at least up the error bars of about 10 to the power minus 8. So there is definitely no condensate, at least given the statistical error bars, which is extremely small, 10 to the power minus 8 or so. And so you can either argue that there's no condensate, or you can argue that maybe there's a condensate like 10 to the power minus 15, in which case there is no hope of determining that using these simulations. But you can turn that around and ask, it looks more likely that it is a conformal theory in the infrared. So can you turn it around and ask, if it is conformal, what is the corresponding scaling dimension of this theory, and what are the properties that you can learn about this theory? One such is that you can, instead of determining the condensate, you can find the derivative of the condensate, which is just the expectation value of the psi bar psi, and then take the derivative with respect to little l. That gives you a instantaneous or L-dependent scaling dimension, and plot it as a function of little l. So this is like, so the point till the dashed line is where the actual simulations have been performed. And beyond that is an extrapolation based on some additive 1/L and 1/L squared corrections. So you see that these are all different scaling dimensions determined from different eigenvalues. And in the infinite volume extrapolation, this is where it seems to go to around 1 or around 1 here. And also these different scaling dimensions determined from 2, 3, 4, and 1, they all kind of converge to around 1. And 1.5 is the CFT unitarity limit. So it seems to be a large enough scaling dimension. And so the QED3 seems to, so the evidence seems to suggest that QED3 has it's a conformal behavior, nevertheless with a large anomalous dimension setting in, and its values are consistent with conformal limits. So instead of the other scenario that there is a condensate. And once we do that, we can look for other quantities and in fact look for what are the consequences if it is conformal. For example, one such consequence has been discussed in the literature is this self-duality of QED3 or n equals to 2 QED3. So the statement, for example, discussed in all these works. So the statement is that if n equals to 2 QED3 flows to a conformal fixed point, so that is important. So the assumption is if it goes to the conformal fixed point, so then QED3 is likely to be self-dual. What does it mean to be self-dual? Is that there is a version of QED3 where for example, if you couple to the background field, it is coupled to the flavor triplet current. For example, B is the background gauge field. And whereas it's dual to a theory, again to n equals to 2 QED3, but this time this background gauge field is coupled to the topological current written here. So there are two versions of QED3 where the B is coupled to different currents. And by taking derivatives, it means that the flavor current correlator and the topological current correlator have to be degenerate. The fact that it's x to the power minus 4 is trivial because the flavor current is conserved. So it's x to the power minus 4, there's no anomalous dimension. And it's because it's non-compact QED3, flux is conserved. So there is again x to the power minus 4 behavior in the infrared. And so the non-trivial statement is that the amplitudes have to match between QED3 and, between the topological and the flavor vector current correlators. So here is one such calculation of the 2-point function of such quantity. So here, these points here on this, it's almost straight line in this log-log plot, is the vector current correlator. As you expect, it's almost a straight line because it's conserved. So there is no anomalous dimension as you flow from UV to IR. So this is the correlator value, and x-axis is the distance between the operator insertions, the 2-point function. And the 2-point function of this the topological current correlator, which is like the Pluckett correlator, is shown here. So as you see, the UV, which is where you don't expect these relations to hold true, it's wildly deviating from the vector current correlator. But as you go to the deep infrared, you start seeing these topological current correlator starting to almost lie on top of the vector current correlator, nevertheless with larger error bars. But you see the tendency is quite apparent that the amplitudes seem to match. Again, pointing to the fact that if to these expectations based on the fact that n equals to 2 QED3 is conformal. So QED3 seems to show again and again a lot of properties which are conformality. And we try to understand this much better in a recent paper is that, let's say QED3, let's not argue whether QED3 in n equals to 2 or a small number of flavors is conformal or not. Let's assume it to be so, and then try to understand why it is so. So as I told you, in the large n limit, it's quite easy to understand because the fermion induces such a conformal term. So it dominates and you have a conformal behavior. Whereas at small n, what happens? There is no reason that this dominates. G squared can start dominating and there's a mass gap. But the fact that we are seeing conformal behavior seems to suggest that led us to hypothesize, or at least ask the question, is it possible that even at n equals to 2, at small as n equal to 2, that it is still dominated, the induced action from the fermion is still is dominated by a bilinear term of this kind, the conformal term, except that it comes up with a coefficient which is not n by 32, which only holds true in the infinite n limit. It's just some random, not a random, so it's some non-perturbatively generated q square of n. It's some function of n. The number may or may not be computed in large n limit, but who cares? So this is all we are saying is that this is the dominant term. There could be subleading f to the power 4th and f to the 6th, which are conformal. But let's hypothesize that maybe what if ask at least what happens if this is a dominant term, with the only condition being that n to infinite limit, this function q square, which I will call charge, the charge, which is a function of n, approaches 32 by n in the large n limit. So this is the idea. So instead of studying QED3, you want to study this system where the partition function is defined as an integral over the gauge fields, and the gauge action is given by this conformal gauge action, which is non-local gauge action. So the point is that the term in red simulates the fermion determinant. So that's the effect of this term, and q square is a variable. And the effect of fermion is simply that is simply the source terms for the fermions. These etas are not dynamical, but simply terms which are coupled to the Dirac propagator, which sees the gauge field generated by this measure. So simply by simulating the fermionic measure of the determinant, we do that by this conformal gauge action. So that is the idea. And change q square and ask what happens. So the proposal is that we studied n equals to 2 QED3, from which we can determine all the conformal properties. For example, the scaling dimension of scalar, the vector, and for example, what happens to the topological current correlators, and so on. What are the amplitudes of these 2-point functions? So those are CFT data that can be determined on the lattice non-perturbatively. So we have them. And now instead do the charge Q lattice model, which is the Q, put Q here and determine the CFT data in this conformal model for the fermionic observables. So that all you mean is you generate gauge fields, measure 2-point functions, 3-point functions, and so on, from just by where the fermions are simply spectators on top of this gauge field. So from that, you can determine the CFT data, and then use these two data in such a way that you match certain conformal quantities, for example, the scaling dimension of the scalar, so that at the charge Q, the scaling dimension of the scalar in the charge Q model exactly matches this charge, the scaling dimension of the scalar operator in an n flavor QED3. So it sets a mapping between a charge Q and a flavor n. So there is no 1/n expansion that's being done. It's a completely non-perturbative matching, because there is no way to get this by perturbation theory. I'm determining it using lattice calculation and then matching it at a charge Q. And once you do that, once you get this Q and mapping, use that to test for other agreements in other conformal properties, for example, 3-point functions, or for example, ask what happens to the distribution of eigenvalues, or ask what happens to whether we are able to reproduce this degeneracy of flavor current and the topological current, for example. So that is what is done here. So in the top panels, what I show here is this finite size scaling of the low-lying eigenvalues, of the first low-lying eigenvalue of the Dirac operator. For example, the different colors are different charges, Q equals to 0.5, 1, and different charges of in the conformal QED model. And so from this, you can determine the scaling dimension, or in other words, you can determine a 2-point function of the scalar correlator, and which is shown here, and then determine from the slope the scaling dimension. So they are consistent with each other. So from this, we can get a gamma S. And in this plot, what I've done is plot this scaling dimension of the scalar with gamma S as a function of the charge Q. So these black points are the determined values of such scaling dimensions as a function of Q. So once you do that, I told you about the QED3 studies that we did. From that, we have an estimate of the gamma S for different flavors, n equals to 2, 4, 6, and 8. And so what I plot here is this: the vertical band is the error bar and the gamma S for n equals to 2, theory 4 theory, 6 theory, and 8 theory, and so on. And so just by mapping it by these intercepts, you have a range of values of Q where you can match the value of the scaling dimension in the conformal model to the n flavor QED3 model. So it induces the dependence of Q of n that I talked about. So from this, you can read out what values of Q corresponds to what values of n. Once you have done that, we can ask what happens to other quantities. Can you reproduce some other properties non-trivially? So one such quantity is the distribution of the Dirac eigenvalues themselves that I talked about earlier. So here I've shown, for example, let's focus on the top panels. So what I've plotted here is the first distribution of the first eigenvalue, second eigenvalue, and third eigenvalue, normalized to the mean value of 1 in all cases. And it's compared with the random matrix model that I talked about by these pink bands, which completely disagrees, which means that this is again reiterating the fact that n equals 2 is not agreeing with random matrix theory. So these actual QED3 lattice values are given by these solid symbols, black and pink points. But instead, if I take this by some value around Q equals 2.5, where it seems to match this gamma S, and I take the distribution of eigenvalue Dirac operators for these values of Q equals to 2.5 on different lattice volumes, and those are the open symbols here. It falls bang on the actual n equals to 2 non-perturbative data, which seems to suggest that instead of a random matrix model describing the low-lying eigenvalues, it's actually a conformal model which seems to describe the lattice data for the n equals to QED3, again pointing out that n equals to 2 seems to like to be conformal in the infrared. Is again another strong evidence pointing to that. And again, for n equals to 8, which is definitely conformal, I don't think there's any disagreement there. Again, when you do this exercise and pick a value of Q, which is close to the n equals to 8 value here, again, it seems to reproduce the distribution of eigenvalues for the n equals to 8 theory. So this is quite non-trivial. Another quantity you can ask is simply to check this self-duality of QED3. Is there some indication of that you can see in this lattice model itself? So again, what you do is use this matching between Q of n, and then so I plot this. So what I've plotted here is this CV, which is the amplitude of the x to the minus 4th behavior of the flavor current correlator. That is the black points here, determined from the lattice model that I talked about. And this blue curve here is simply the prediction for the CV top, the topological current correlator, which is a trivial quadratic in Q square, so which you can compute simply analytically here. So as you see, what happens is as you change the number of, as you increase the Q, which is to say decrease the number of flavors via this plot, by the mapping, this CV starts decreasing and intersects the CV top at a value of charge Q around 2.5. And from this map, we know this Q equals to 2.5 corresponds to n equals to 2. And that's precisely the point where they get degenerated, where the flavor current correlator gets degenerated with the flavor topological current correlator, which is a prediction of the self-duality. Again, we are able to capture it. So we saw evidence of that in the actual QED3 calculation, and we are again able to reproduce it simply based on a quadratic conformal gauge action, simply by the unknown Q square tuned to n equals to 2 value. So these are all, through this mapping, which could be approximate, I'm not saying it's an exact mapping, through even in such an approximate level, we are able to capture a lot of behavior that is seen in QED3, and again points to the fact that maybe Q equals to QED3 is quite conformal in infrared, and also it's quite a good understanding of what's happening. And turning ahead, so instead of asking for this mapping between QED3 and this lattice model, we also think that this lattice model, this bilocal conformal model, by itself is a nice model to play on the lattice with. And for example, it's quite hard to even extract the scaling dimension on the lattice, but here you can generate the configurations without any correlation. It's quite nice by Fourier transforming. And that means that you can go to quite large lattice sizes and even measure 3-point functions, which are quite interesting to CFTs, and extract, for example, put 3 operators and ask for the coefficient, which is the 3-point function Wilson coefficients on the lattice. And I've given an example of what happens if you put vector and scalar vector type 3-point functions. And then so just multiply this whole 3-point function by the expected scaling in the denominator, which is quite typical, which holds only in a CFT. And then you can, and so you would expect that when the distances between all these correlators increases, you should see a plateau as a function of the distance scales. And you see that indeed there is a distance scales, and through these future works, maybe you can extract these 3-point function coefficients on the lattice itself.
You've got 5 minutes left. Yes.
Yeah. So through this, some future works, which we are trying to understand is what in this model can we even understand the 4 Fermi operator scaling dimension, and that's something we have to study and show that maybe even the 4 Fermi operators are turning out to be irrelevant. That is something which is noisy, and so that a lot of work is required in this direction. But at some point, we would like to do it, and also can we kind of extend this to compact model, where you expect this to be confining for small enough charges and deconfined for large enough. These are all things that's interesting. So in the remaining minutes, what I will do is try to say what happened. What can we study the topological different scaling dimensions? So it's so the motivation for understanding the monopoles is simply compact QED3. And for example, the work for Polyakov showed that when there are no fermions, the gauge theory is confining for all values of the coupling. And what happens is if you introduce the fermions, is the confinement lost, or is it at what critical value is it lost? But the point is, the pure compact theory itself doesn't have a well-defined continuum limit at the Gaussian fixed point. So you can study that any finite lattice spacing, but there are no lines of constant physics that you can do. So it's quite difficult in the way we are doing this calculation. So in order to do that, maybe in the future, what one has to do is study a well-defined model, for example, the SU2-Georgi-Glashow model, and then try to recover the compact QED in certain limits. Maybe that's for the future. But instead, the easier approach is an indirect approach. So we can do the non-compact QED3. So and I showed that it's quite likely that it's conformal for all values of n. Now, at the infrared fixed points of these n-flavor non-compact QED3, we can ask what happens to the monopole operators in the non-compact QED3. What I mean is there are no monopoles that are popping out in the gauge in the path integrals for non-compact QED3. But because it's a U1 theory, you can introduce monopole operators as spectators. It's just an insertion in the theory. For example, it's like a 4 Fermi operator insertion. It's not there in the theory, but you can put the theory and ask for the correlation functions. So similarly, you can do it for the monopole operators and with the charge. So that you introduce 2 points so that you have a flux Q around the 2 of the ends, and then ask what happens if you change the distance between the 2 monopole antimonopole pairs and how does it scale? So it's interesting because once you do that indirectly in non-compact QED3 for large n, you would expect that compact and non-compact the monopole operators to be irrelevant, and so the compact QED3 would also flow to the same infrared fixed point as the large n non-compact QED3. But as you lower the number of flavors, at some point the monopole operator, the lowest monopole operator, will start becoming relevant, and so compact QED3 will no longer flow to that fixed point where the non-compact QED3 flows to, but instead it will either flow to some other fixed point or generate a mass gap. So it's an indirect way to estimate what's the critical value of flavors. So the way to do it, so as I told you, it's not easy to introduce monopole operators because when you write it in terms of it's defined easily through its action, but it's harder to write it in terms of fundamental gauge fields and the fermionic fields. So you have to do it. For example, so it's quite non-trivial. So the way we did it is to say couple a Dirac monopole antimonopole background gauge field to the non-compact QED3 and ask for the ratio of the partition functions with the gauge field turned on with respect to gauge field non-zero. So this ratio gives the monopole antimonopole scaling correlator. So if you change the distance between the monopole antimonopole pair, you would expect this correlation function to scale as out of the delta Q, where delta Q is the scaling dimension. So the way to do it is you cannot simply do that. But you can do the way to do it is to differentiate and then integrate. So the point is the point of differentiating first is that it reduces to a correlation to a quantity which you can compute in the Monte Carlo, which is this quantity which is determined here, and then you integrate it from and do the simulation of QED3 with each value of this auxiliary variable zeta and integrate it from 0 to Q. And one such example for example, the case I've shown here is for the XY model. And so I've shown here how this derivative of partition function with respect to zeta behaves. So you integrate these quantities, you can go all, if you do till integrate till 1, you'll get Q equals to 1 monopole, 2 is Q equals to 2 monopole, and so on. So it's easier it's not easier, it's computationally expensive, but it's straightforward. So here's a plot of such a correlation function in QED3. So it's on the y-axis, I've shown the logarithm of the 2-point function of the monopole antimonopole correlator, where the distance between them is kept fixed in box size. It's always kept to be proportional to the box size, which is L by 4. And then the box size is varied. In n equals to 2 theory is shown as in red, n equals to 4 theory is shown in black, and n equals to 12 theory is shown in blue. So the n equals to 12 theory, you expect it would be close to a large n expectation. There are calculations of monopole scaling dimensions in large n limit, for example, a calculation by Kufu. And indeed, when you try to fit this data, it's quite consistent with a large n expectation. So, but in n equals to 2 and 4 is are small n's. Now the question is what happens there. The large n predicts that the first correction to the free field theory value is actually a negative quantity. And in the large n limit, what happens is, it's because it's negative for the n equals to 2 theory, the scaling dimension of the first q equals to 1 monopole actually becomes less than 0.5. And because it's a scalar operator, it's a Lorentz scalar, it is bounded by minimum value it can obtain is 0.5. And so for in large n limit n equals to 2 theory, the monopole scaling dimension is actually less than 0.5 in large n expansion. So it was one such indication that maybe n equals to 2 QED3 was not conformal. But instead, what is happening in our actual non-perturbative calculation is that even though n equals to 12 agrees with large n limit, the 4 and 2 seems to deviate from the large n limit by a positive number instead of a negative number. It's a small quantity, but nevertheless, it's positive. And in such a, so the first thing to notice is that the n equals to 12 value comes out to be, q equals to 1 monopoles comes out to be 3.2. So it makes that n equals to 12 is actually coincidentally is the marginal value where the monopole becomes relevant or marginally relevant. So the critical value in compact QED3 where there could be a transition between the scale invariant and conformal scale broken behavior could be around 12, about plus or minus 2 to be conservative. But as I told you, for n equals to 2, this, because it's a positive correction that we see on the lattice, it turns out to get a value around 0.8, and that's larger than 0.5, and 0.5 is a unitarity limit. So this is yet another way. There's still more. There's again a consistency check that your scaling dimensions are satisfying behaviors that are expected. So, and it's a non-trivial way, the q equals to 1 monopole in QED3 also turns out to be have a scaling dimension just greater than 0.5. So, and q equals to 2 is a trivial thing to do, and as we learned from David Poland's talk, and so the way they map is q equals to 1 and then ask for q equals to 2 and then their phase space. These are all things that we can do on the lattice, and hope in the future we hope to do those steps. So I will end my talk here. So that's a good stopping point for me. So if there are questions I can ask. So I have the things that I didn't cover is how to put the Chern-Simons theory on the lattice. For example, the dualities there are a lot of literature on the dualities in the continuum. It's extremely trivial to write on the lattice those dualities in terms of the determinant of the overlap operator, simply by the fact that V is a unitary operator, so the determinant of V is a phase, and that phase is nothing but the Chern-Simons term. So all these Chern-Simons term and the mixed Chern-Simons term and such fermion plus U1 k-half that you see in the literature can be converted into a lattice statements. The only problem is how to do a simulation, because there are sign problems. So there these problems could be quite interesting to people in the audience who are interested in sign problem-based problem, which are quite relevant to a lot of issues in high energy physics. So yeah, so I stop here and I'll just flash the summary slide, answering a lot of questions I started with and kind of give an answer to each of them. Thank you.
Thank you very much, Nico, for this great and clear talk. So I'm applauding for everyone. So I guess there are questions. So yes, Simon, please.
I have a question. Yeah. Thanks, Nicola. That was a really nice talk. You were discussing the self-duality of the two flavor theory, and your kind of evidence you produced was the matching of these two current correlators. Mm-hmm. And the key point seems to be that it's not just the way they scale with the separation, but it's the prefactor. Now I can believe that the flavor current is exactly conserved, but did I understand what can you say about? It wasn't too clear to me that what you're calling the topological current would be conserved on a lattice. So
it's the F mu is a Pluckett correlator. It's the F mu.
Yeah. So normally these things have big corrections when you're trying to match them to continuum expressions.
Yeah, so that's true. So you do have to smear it and like try to see, and then try to do it. See if you do this calculation on different sized capital L's, which are different lattice spacings, how well they are. So the calculation that I showed here in actual QED3, this is a calculation at L equals 20, but we did calculations with different capital L's, which is to say different lattice spacings. There are not much deviation there.
So you're claiming that the topological one will join eventually as you go on to a fine enough lattice. Is that what you're saying?
Oh, not fine. The point is you need to take a large physical box size. Yeah. And yeah, so if you take the continuum limit and everything is taken into account as you take the box size to infinite, that the indication is that it will join the flavor current. Yeah. Okay, I can kind of believe it, but you're on a log-log scale there. So I think the question of whether the amplitudes match, I think, is of course. I mean, the log-log plot, the error bars are small, but in the actual scale, the error bars are also large. But in the error bars, they are consistent with. We take the ratio. It's quite consistent with 1. So here the conclusion is it's just an indication that it's happening. At least it's not terribly. What could have happened is you start here and it just some curve here, where the x to the power minus 4 behavior, but that's not happening. So at least it's quite promising that it's a curve which is lying closer and at least showing some indication that it's getting degenerate. Yeah. Okay. I'm just trying to understand. Yeah. Thank you.
Yes, there's another question by David.
Yeah, let me ask just a quick follow-up question. Can you go back to your plot about showing these coefficients in the current 2-point functions?
So in QED3 or the
in QED3? Yeah, I was curious if did you compare these with the large N predictions for the coefficients?
Yeah, so okay. So here's while you can compare for example, the anomalous dimensions and so on, these depend exactly on how you want to, this depends on the model that is the normalization of the fields and so on are determined by the model itself. So within this model, the CV seems to decrease, but there should be some Z factor which maps the operators in this theory to the actual QED3 model, operators that appear in the QED3 model. That is something unknown. But so working entirely within this model, where you don't have to worry about those conversion factors and so on, you see that these amplitudes are consistent within the model itself. So that was the point I was trying to say. And for the QED3, actual QED3, we did compare with the large N model. So that predicts that the coefficient of CV is a positive quantity. It actually goes above the free field theory value. And at least within the error bar, which is large enough, we see at least indications that in the infrared limit, the lattice value of the CV seems to go below 1 and not above 1.
So I see. So the issue is that your definitions of V mu and V mu top.
That problem does not.
Maybe some normalization factor that you're not.
So within QED3, there is no problem. The whatever we studied as QED3 on the lattice is the continuum QED3. I mean, up to, yeah, we did everything correctly. Once you have done that, then the CV that we measure in the actual QED3 calculation is the CV in the continuum theory that you're interested in. And in that calculation, which I didn't have a plot of, I mean, just related to this plot here, if I simply plot CGV times x to the power 4th and see how that coefficient changes as you go from small UV to IR, that has a mild tendency to go below 1. The IR value seems to be lower than the value in the UV, whereas in the large N limit, that behavior is the opposite. But they are extremely tiny numbers in either case, so more work is required.
Right. So for the infrared fixed point, there's also there are calculations of CV in the 1/n expansion.
Yes.
That you can compare with.
Yeah. That is a positive correction. That's right.
That's a positive correction, right? Okay. All right. Thanks.
There's another question by Shailesh.
Hi, Nikhil. Nice for a good, interesting talk. one question I had was about understanding a bit about lattice errors. So if you're trying to do a conformal field theory, if you're in sort of continuum, the L, the small L is just the size. And so it's just introducing a scale in the problem. So in some sense, it just is not important. You can choose any L and everything sort of scales with, like, if you're looking at an energy, it scales like 1 over L. But in a lattice, I would argue that maybe there is another scale which is coming from the lattice spacing. And so you need to sort of go to small enough lattice spacing where all the corrections go away. Now that depends, I guess, on some operators that come in from the lattice scale or something like that. So in your calculations, how big a lattice will sort of, for example, are the lattice spacing errors some A squared or A?
Yeah, so yeah, that's true. So let me try to answer your question. So as you said, like, so you want to use as large. So when I say lattice spacing, you want to keep little L fixed and then take capital L to as large a value. So you want to scan a whole set of capital L's, right? Right. So you want to, I mean, in principle, you might want to keep it even smaller than 1 and so on, right? So as small as possible. So what we found here, at least for example, I can argue empirically that, so if you keep capital L, even up to little L of 250 on a capital L of 28, it shows a good scaling with respect to the lattice spacing. So the expected scaling for overlap is A square, so it shows a square dependence. And so we did cross-check it. For example, this could be, we are just fooling ourselves. So what we did is, we also did this calculation with the overlap fermion as well as the Wilson fermion. For example, the difference is that the overlap fermion has an exact flavor symmetry. So the Wilson fermion only gets the flavor symmetry in the continuum limit after you take the continuum limit. So there is no reason that if you did a really bad extrapolations and so on, there is no reason that the lattice calculation from the Wilson has to agree with overlap at each given little L, which is physical units. So when we did this calculation, so the overlap exactly falls on top of the Wilson extrapolated values. So there's one more evidence to the fact that the extrapolations are working well. So one reason that you could, for example, use a coarse enough lattice to get you don't have to go to extremely fine lattice, is because
that's the interesting question. Why?
The QED3 is tending to be conformal, right? So there are no, the why it won't work in QECD is that, for example, if you took an extremely coarse lattice, because there are particle spectrum, for example, the proton mass times the lattice spacing will be something like 2, then within one lattice spacing, you would just see it going to 0. So you better make sure that your errors, the lattice spacings are fine enough. But that's not happening here. What is happening is that the masses at any finite little L turns out to be just proportional to the little L itself. So that because there is no masses and it's an extremely tiny number, even even if you use a coarse enough lattice, n times A is smaller than 1.
So if I flip that, so if I flip that question around, and let's say I use your coarsest lattices, right? Let's say I just I'm a very poor man. I don't have big computers. I'm going to just use the smallest lattices that I can work with. Okay. I guess you're demonstrating that even with that, maybe with, I don't know how many percent error, maybe 5%, 10%. What is the error that you would make if I just lived in that smallest lattice to get the physics of a conformal field theory? I guess that's my sort of flipped question, in the sense, can we, if I'm willing to live with some errors, right? Can I live with a very, very small lattice and still get good understanding of what's going on, maybe within some errors? So what is the smallest lattice I would say you could work with if I allow you, let's say, 5% errors or things like that? Do you have a sense of that?
Okay, let me see if I say a little L of, you want to work with a little L of 1 by just till this point, which is this extremely small lattice volume, but extremely fine lattice, right? So here you would not be able to. So so it depends on until what is your what point you allow this calculation. So if I do that, I mean, I have to see what happens if I skip these points and so on. So basically, this is the answer to your question, right? So it depends on, you want to skip these points here and then do an extrapolation simply based on these points, in which case your errors will blow up, right?
So maybe I don't understand this curve. So I thought that L should only enter in a very simple way, right?
Sorry,
and the small L should enter only in a very simple way, right? So in a sense, it should all go like 1 over, oh, this is gamma of L, right? I'm sorry.
Little L is the physical box size that you're interested in. So you want to choose physical box sizes in such a way that using a capital L cube box size, it's really fine enough that you are comfortable with that, right? So smaller the box size means you can work with extremely fine lattice, and given a computational power, more the little L you use, the lattice size, the typical range of lattice spacings that you're using for extrapolations are also getting coarser. So it depends on, so one way to argue it is that you want to use only fine lattices, in which case your systematic error would be extremely large. The other case is simply to say, let me cross-check the result. Let me go to this point and cross-check as many ways as I can. And one non-trivial cross-check is simply use different kinds of fermions and see whether you're able to reproduce whatever you have seen. And that's the test we have seen. And it seems to work. And the reasoning is simply that there are no masses in this theory. So the masses, so the important quantities are, if you measure the lattice spacing in units of the masses that are appearing in this theory, these are all extremely small. So all the correlation functions extend to large enough decay over a large number of lattice points, even on a little L of large, because the masses itself decay as 1 over little L in a CFT. It doesn't decay in one lattice spacing. So so as far as the degrees of freedom in some sense concerned, they see a much finer lattice over their Compton wavelengths. So I think that is the reason that it's actually working.
Okay, yeah, thank you.
Okay, so there is another question by Rajamani.
Oh, it's not a question. Oh. I thought I would just remark one more thing with respect to what David asked. So the way we did the 3-point function, we normalized it with respect to the 2-point function. So those coefficients, the things that come in front of the 3-point function, they are intrinsically correct. They don't depend upon the Z factor.
So I see no further questions, comments.